Okay, guys, back again. So yesterday we talked about, well, I say yesterday, let's be honest, it was about 30 seconds ago when I finished my last video. But anyways, yesterday we talked about speed ratios, how the size of one gear or pulley is in direct ratio with the speed of another gear or pulley in that same system, connected by chains, belt, or interlocking teeth. Today we're going to talk a little bit different. We're going to talk about how torque is changed. So we'll start out with a diagram to kind of demonstrate what we're doing. It looks a lot like our diagram yesterday. So this is pulley 1, this is pulley 2, we have our belt connecting, and I'm going to draw something a little different here. We have a hand with a broken thumb, apparently. There's a hand right here holding the belt. Now, suppose this is my hand, and I'm grabbing this pulley, this belt in between the pulleys, and I'm pushing that direction. That's not a direction. That direction at 100. Make sure you can read this. 100 pounds of force. Okay, so this would mean that there is 100 pounds of force on each pulley, since the force is equal to all the points along the belt. So if I grab right here and try to turn this at 100 pounds, is the same thing as if I grab it down here and try to turn it at 100 pounds, or if I grab the side of pulley number 1 and try to rotate it with 100 pounds of force. It's all the same, because the force, the point of force is the belt. If I push here at 100 pounds, that means 100 pounds of force is moving on this side. So kind of keep that in mind. If you recall that torque is the product of force times the lever arm over which the force is applied, or that equation we used is TO equals F times LA. In this case, F is the force or tension on the belt, and the lever arm is the radius of the pulley. So what does that mean? I'm just going to use the numbers in the book. If you're following along, I'll change colors for us. So if you remember, torque is a measurement that is measured, it's force times the applying lever arm, that's F times LA, but it's measured at the point of rotation. So that would be in the middle of these pulleys. And, change colors again. So we have a force that's 100 at every point along this belt, and our lever arm is this radius. So, I hope you can kind of start to see something that's unfolding here. Even though we have the same force, we have different lever arms, and that means that our TO, our torque, and our F times LA equation are going to be different. So let me go ahead and write that up here just so we have it on the top of our mind. TO equals F times LA, right? TO equals F times LA. Well, in this case, we have the same F, force is 100, but for side 1, it's going to be bigger than side 2. So I'm just going to kind of go along with the numbers they have in the book. If we say the radius, we'll go back to the same things we had yesterday in the last video, our diameter equal 10 inches, and on side 2, our diameter equals 5 inches. So that means, but we're not worried about diameter, we're worried about radius, is what we're calculating with. Radius equals 5 inches, and radius equals 2.5 inches. 2.5 inches. There we go. So we plug these in on side 1, so I'm going to say TO1 equals 100 times 5 equals 500, and we look at our measurements. This is going to be in pound inches, and over here we have TO2 equals 100 times 2.5 equals 250 pound inches. Okay, so that's something, right? Now, if we remember back yesterday, what were those? We were turning at, was it 100 RPMs? Yeah, this was turning at 100 RPMs. So on side one, we know, I'm just going to rewrite all this. Diameter equals 10 inches. Radius equals 5 inches. Our RPM, if our RPM was 100 on this side, it's not a measurement, and our torque, TO equals 500. On this side, we have diameter of 5 inches. Let me erase this. Diameter of 5 inches, that means a radius of 2.5 inches. If you remember yesterday, our RPMs were twice as much. So 200 RPMs, and our torque we just measured, RPM equals 250. Okay, so let's stop for a second. Let's just look at this relationship and just see what we notice here. So we notice this pulley 1 is twice as big as pulley 2. Same thing if you're looking at diameter, radius, whatever, it's the same, it's twice as big no matter how you cut it. Now that gives us some measurement here. That means that in this system, because pulley 1 is twice as big, it turns half the RPM. It's turning 100, where RPM 2 is turning 200. But it's turning slower and it's larger, so it has a longer lever arm. So that gives us a measurement, a torque measurement of 500, where pulley 2, which is turning twice as fast, only has a, sorry, wrote the wrong notation, a torque rating of 250 pounds. That's kind of interesting. What I want you to get here is, now granted, these are the simplest numbers I can come up with. This one's twice as big, this one's half the size, so the numbers are nice and easy to work with. It's not going to be the case on your exam all the time, but it tells us something, right? This is twice as big, so it turns half the speed and has twice the torque. It has less speed and more torque. Whereas side 2 is half the size, turns twice as fast, and has half the torque. Okay, so that's interesting. What does this mean? That means if we use bigger pulleys, we can have more torque. So think back to our bicycle example we talked about. If you have a bicycle, maybe you want to go out and look at it, the back cog, so say this is our drive wheel, we've got pedals and feet attached to this side, and this side is connected to the back wheel. The larger the back sprocket that your chain is on, the lower gear you're in. That means you're not going to go as fast, you're going to move slower. Because it is getting bigger compared to the smaller sprockets on the same axle, but you're going to have more torque. So that's why you gear down, you move your chain to a larger sprocket when you're going up a hill. You go slower, but you have more power to go up that hill. If you try to climb a hill on your bicycle in top gear, you're gonna peter out of energy pretty quick, right? Well, that's exactly what's happening here. You lower your speed to increase your torque. Same thing on cars. If you're trying to pull a trailer with a truck or a tractor, you gear down to a lower gear to get more power. You're going to go slower because you're moving to a bigger gear, a lower gear, but you're going to have more power. You think about it, when you're at a red light and you're trying to race the guy beside you. I don't know if any of you guys do that or not. Surely not. You take off and you're going and he's starting to gain on you. What do? You drop a gear to give you more power, more of a push. So you drop a gear to get more power. Same thing when you go up a hill in just any kind of automatic car. You go up a hill, your RPMs get low enough, and then it drops a gear, the RPMs change, and it gives you more. You have to turn more RPMs to keep the same speed, but it gives you more power. So we have a direct relationship, once again, that we can look at. We can have a direct relationship between torque and speed. That relationship is, we'll change colors, TO1, me erase all this. I'll probably regret erasing that here in about 2 minutes. Times RPM1 equals TO2 times RPM2. Okay. So let's give an example. Once again, I'm going to use the one out of the book. TO is torque, RPM equals the RPMs. So say we have, I'm not even going to draw different sizes. So these are not anything to scale. I'm not even going to draw the sizes. But say on sprocket 1, we got sprocket 2. On sprocket 1, our torque is 20 pounds. And our RPM is 300. On side 2, we don't know our torque. Torque is our variable, but we know our RPM. It's 50. Okay, we can take this and do plug in this equation to use our simple algebra to figure out what this problem is. So that gives us 20 times 300 equals TO2 times 50. So that'll be 6,000 equals TO2 times 50. Divide both sides by 50. And we end up with TO2 equals 120 pound-feet. 120 pound-feet. Okay, so what do we know? We filled in, we know by the speed of these two that this one is going to have more torque. What does that tell us? That tells us that this is going to be a bigger diameter. Now, could we calculate diameter with this? I want you to think about that for a second. Could we calculate the diameter of this? No, we can't. Anybody know why not? Because we don't have the diameter of side 1. Now, if I said that diameter of side 1 was, 12 inches, yes, we could figure out the diameter of size 2. It's the same, going to be 6-to-1 relationship, so it would be quite a bit bigger. But as of right now, we aren't given a diameter, so we can't calculate it. This is the principle upon which tractors operate. An engine runs at high speed with low torque, and the axle turns at low speed with high torque. The transmission, therefore, reduces the speed of the crankshaft in the engine, thereby amplifying the torque available at the wheels of the tractor. So think about a tractor. A big tractor, a very big tractor, is 150 horsepower. I mean, that is a monster. That is a very big tractor, especially in this part of the world. That's a big tractor for most parts of the world. A small truck, say a Chevrolet S10, it has about 210 horsepower. My S10 truck has 210 horsepower, or that's what it's rated for. So if we look at power, the amount of work we can get done in amount of time, the S10 can do more work than the little S10 can do more work than that huge 150 horsepower tractor. But we all know if you take a 150 horsepower tractor and connect and have a tug of war with an S10, it'll drag it all over the place. I've got probably a 40 horsepower tractor will drag an S10 all over the place compared to 210. So why is that? Well, because these principles of lowering RPMs to torque, to increase torque, are what tractors are made to do. Their tires turn really slow. You don't drive a tractor down the interstate. If anybody's ever gone 25 mile an hour on a tractor, it's a life-altering experience. It is crazy fast on a tractor. If you've gone 25 mile an hour in a car, you're driving Miss Daisy, all right? So cars are made to drive much faster, but because the RPMs of the wheels are so much higher, even though they have more overall power, they have a whole lot less torque. That tractor with less torque is going to have much more, with less power, is going to have so much more torque because it's geared so low. So that's how you can take an average, an average or a small tractor, say a 50 horsepower tractor, and you can pull pretty much any vehicle in a tug of war that's on the road today. All right, now that's all we have for today. I'll see you later.